Test. Okay, so some things that you need to keep in mind is the VSEPR shapes, the electron geometry, the molecular geometry, and intermolecular forces. So looking at part A, we have to draw the Lewis structure, know the bond angle, the VSEPR, and identify whether the molecule is polar or nonpolar. So I'm going to draw the Lewis structure first. So for carbon, there are 4 valence electrons, and for hydrogen, there's 1 electron for each. So since there's 4 hydrogen, there's a total of 8 electrons. So we're going to put carbon in the center because it's the least electronegative, and we're going to draw in the bonds. With the 2 dots, it requires 2 electrons to draw a bond. This has 4 domains, so this is called a tetrahedral. A tetrahedral has a bond angle of 109.5, and I believe in your notes it says 109.5 and some of it says 109. I'd be happy with either. None of the hydrogens are pulling harder than the other, so therefore this is non-polar. For chlorine gas, each chlorine has 7 valence electrons, so therefore it will have 14 electrons total. And so we're going to draw in 2 electrons to connect them, and then draw in the other electrons. And we have 14. It's linear, so it's 180 degrees. It's linear. Now both chlorines have the same electronegativity, so the difference between the two makes it 0, so it is nonpolar. Then we have SO3. So this one, we're going to look at sulfur having 6 valence electrons. Oxygen each has 6. So there are 3 of them, so it's going to be 18. So we're going to have a total of 24 electrons here. This one's going to look like this. This one has resonance. Resonance means that there's more than one correct way of drawing it. And so with the resonance, you need to draw each of them. And so we're going to draw the double bond on the other oxygens. We want to make sure that we draw in those Lewis dot structures. The lone pairs as well. And then lastly, there's one more. And be sure to draw in those lone pairs. Okay, so this has got 3 electron domains. So this is going to be trigonal, planar, and this is going to be, since none of the oxygens are pulling harder than the other, then we call it nonpolar. But in reality, with the double bonds, the difference in bond length changes. And with double bonds, it gets shorter. With the triple bond, it gets even shorter. And so then that does play a little bit of a role. But we're going to categorize it as nonpolar for my class, please. And then this is going to be 120 degrees. Okay, so now this part B, we have to identify the Lewis structure, and then we have to identify the VSEPR molecular shape. So now molecular shapes means it changes from the electron geometry, because if there's a lone pair, it's a different shape. And then we have to identify the intermolecular force. So NH3 is known as ammonia. Nitrogen has 5 valence electrons because it's in the 5th column. Hydrogen has 1, and there's 3 of them, so there's going to be 8 electrons. So we're going to draw this one in like this. I'm going to be a little bit lazy because the dots are going crazy. I'm going to draw lines instead. So now we've got 4 domains, but 1 lone pair. So this one's going to be called pyramidal. And another term that you might see is trigonal pyramidal because it's 3-sided. And then The intermolecular force, well, it's either hydrogen bonding, dipole-dipole, or London dispersion. Because of the lone pairs, this is definitely polar, so it's not London dispersion. London dispersion occurs between nonpolar molecules. It's either dipole-dipole or hydrogen bonding. So let's look at hydrogen bonding. Hydrogen bonding occurs between hydrogen and fluorine, hydrogen and oxygen, and hydrogen and nitrogen. Well, looky here, we have nitrogen. So this is going to be hydrogen bonding. Okay, SO4, -2, sulfate. This one's fun. So we've got a polyatomic ion. That means we're going to count the electrons, the valence electrons, and then add 2 more because it's got a charge of -2. So sulfur has 6, oxygen each has 6. There's 4 of them, so it's going to be 24 plus 2. So we're going to have a total of 32 electrons to play with. Excuse me. This one, we've got there's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, and then we put a square bracket around it and put the -2 outside. And this is going to be tetrahedral. So this is actually going to be ionic, an ionic dipole. And that's because it's an ion. And so if it were to attach itself or be attracted to other molecules that are covalent, it would be an ionic dipole. So I just realized I have to draw in the dipole moment. So what is the dipole? The dipole means what direction are the electrons going in. So I'm going to see if I can change the color of my ink so it's easier to see because it's getting a little messy. I'm going to make it green. Okay, so now I'm going to look at the electronegativity values, and looking at ammonia, nitrogen has a higher electronegativity value than hydrogen. So they're all going to go towards the center, and then the lone pair is actually going to pull it up towards the nitrogen. So it's all going towards the nitrogen's direction. For sulfate, oxygen has a higher electronegativity. So the dipole moment is going out towards oxygen. Okay, let's look at the next section, part C. Part C, we're going to write the formula. So water is H2O. It's Lewis dot structure. Well, hydrogen has 2, oxygen has 6. We should be very good at drawing water at this point. It's electron geometry. There are 4 areas in which electron pairs sit. So 4 areas means it's a tetrahedral. And then it's molecular geometry. Remember, the name changes if there's a lone pair. So for a tetrahedral with 2 lone pairs, we're going to call it bent. For carbon dioxide, it's CO2. Carbon goes in the center, oxygen on the outside. This one's actually double bonded. And we can verify the number of electrons that we drew. Carbon has 4, oxygen has 6, and there's 2 of them, so it's going to be 12, so there should be 16 electrons, and I have 16 electrons drawn. This one is linear for the electron geometry, and guess what? It's also linear for the molecular geometry. Okay, so now we got an extra credit section. So for this one, we're going to look at the number of electrons that we have available. For this one, selenium is in column, I actually have to look it up. I forgot. 1 second. Oh, column 6, so 6 valence electrons. So fluorine has 7. So this one's going to look like this, and I'm going to draw in lines for the bonds. Remember, each bond is 2 electrons. And then we're going to draw in the lone pairs for fluorine. And so selenium has 6, fluorine has 7, there's 4 fluorine, so we have 28. So we should have a total of 34 electrons. Is that correct? That is correct. Okay, so let's make sure I have 34. Each line is 2, so that's 8. Then 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. Oh, I have too many. Okay, that one goes away. So if I have 5 domains, good thing I checked, 5 domains, its electron geometry is, well, let's look at our key. It is trigonal bipyramidal. And then its molecular geometry with 1 lone pair is seesaw. Okay, sulfur hexafluoride. Sulfur has 6 hexafluoride. That means I have 6 fluorines. So this one's going to be, well, each fluorine has 7. I'm going to multiply that by 6, so that's 42. So we have a total of 48 electrons. I need more space here. The Lewis structure is going to look like this. This one's going to be called octahedral. In fact, it's octahedral for the molecular geometry as well, because there is no lone pair. Okay, so that's it. I hope that was helpful.